Hello again, chemistry. We're back for another episode of Coronavirus Chemistry. This is your Tuesday lesson after the topic of phase change. We're actually going to continue to talk about phase change, but from a energy cost kind of way, and also from the perspective of what is physically happening to the molecules that are involved in the phase change. So let's go through this together. I've made up my notes for the lecture, and let's talk about what's happening here. So, of course, when something is changing in phase, either like a solid going to a liquid, there's got to be energy going into the compounds to do that process. And so, when you are going from a solid to a liquid to a gas, heat has to go in, and so warms up the substance. Or if something is cooling, so a vapor condensing to a liquid and then going into ice, that would be an exothermic process, and that would be the cooling process, and energy would be taken out. So if something is heating up, energy is going in. If something's cooling down, energy is going out. Energy going in means endothermic. Energy going out means exothermic. So when a substance is changing phase, it has to go either through an exothermic or endothermic process. Now, the molecules that make up the substance, whatever that is, maybe a cup of water or something else, I can't think of anything right now, but we're going to talk about water mostly here. Those molecules are attracted to one another. They're attracted to one another based upon the fact that they have what are known as intermolecular forces with one another. So IMFs, I might use that phrase in the next few minutes. IMFs. Those IMFs are what hold those molecules together. Either as a solid, the IMFs are very strong as a solid, keeping the molecules locked in place, not moving very much, or as a liquid, where the molecules can slide past one another. They still are pretty strongly attached to one another. They are connected by the IMF, but they're not quite as rigid as what they would be in a solid phase. Or the last kind of phase, of course, gas, where the IMFs are actually really weak, and so the connective forces between the molecules are weak, and so the gas molecules spread and get away from each other really, really easily. Now here's a picture of what's happening with water. So water, as you recall from our topic of VSEPR and stuff like that, water is a polar molecule, and so it's shaped like this V here. And because water is polar, it has a dipole. Remember, a dipole is where one side of the molecule has a very strongly electronegative element and the other side of the molecule does not. In this case, remember, oxygen is very electronegative, and so the electrons involved in this covalent bond here are going to be pulled towards the oxygen atom, and therefore, since the electrons live over here on the oxygen, the electrons are negatively charged. The oxygen side of water is negatively charged. And then the hydrogen side of the molecule, the electrons do not spend as much time there, so it's a positive charge to the hydrogen side of the molecule. And then water molecules can line up such that they will repeat because positive and negatives are attracted to one another. So you can see this in this picture here. The oxygen side is negative, the hydrogen side is positive. So if another water molecule were to come along to link up with this water molecule, this water molecule is going to arrange itself so that the oxygen is closer to the hydrogen side because positives and negatives are attracted to one another, and so on and so forth. All the water molecules are going to line up in that way. They're never going to break that. That is a fundamental fact of how charges work. Positives and negatives are attracted to one another. So that's how the waters are going to arrange themselves. No ifs, ands, or buts. So when water molecules are arranged this way, as a solid, they're going to be really close together, and then as a liquid, they're going to move past each other and slide past, but they're never going to really get away from one another. And then as a gas, they're going to eventually escape from one another. The IMFs get really weak as a gas because there's a lot of heat going in, and so the connective forces, those IMFs, are going to be weaker because of all the energy, and they're going to pull away from one another. So in order to do a phase change, the intermolecular forces have to be broken, and the only way they can be broken is by adding sufficient heat. You have to heat up these compounds, make them have a lot of kinetic energy, and so that the amount of energy in the motion of these molecules is not sufficient is too much. Let's say it that way. Is too much for the IMFs to keep them contained. So think of it like a rubber band. If you have something on one end of a rubber band, and this molecule over here is trying to hold on to that rubber band, this guy is moving so much of the high kinetic energy, eventually it just snaps, and the molecule here is going to go off and be in a gaseous phase, and that molecule over here might do the same thing. Depends on what's going on. But it's kind of like a rubber band. The IMFs are holding the molecules together, but if you have the molecules going crazy, eventually it snaps apart, and you're not going to have any connective force between them. So with that, we can talk about, well, how much energy is there? Is necessary to break those IMFs? Those values have been determined, and I want to go through this picture right here. So we have gaseous water, liquid water, and solid water. Solid water, as you can see, is like an ice cube. It's a cube. It's a solid, rigid complex of water molecules. And then liquid water, which you and I always drink. I've got mine right here, as usual. The water molecules slide across one another, so they're no longer in this rigid complex, but they are still moving around, and they're connected to one another. Those IMFs are still present and strong enough to keep them close together, but not locked in place. And then as a gas, the water molecules can fly off, and the IMFs are really pretty weak at that point, and so they can't. They're never going to really condense until energy is removed. We're going to slow down these molecules in order for the IMFs to take over and control their movement. The amount of energy that is required to get water molecules to go from this state to this state is known as the heat of vaporization. So heat of vaporization, delta H VAP, equals energy needed per mole to vaporize a substance, to liquid, or to make it into a steam. So taking a liquid and turning it into a gas. That is known as the heat of vaporization. It is a number that is just how much energy per mole is required to get that liquid substance to become a gas. In the same way, we have the heat of fusion. And a lot of times people think, oh, fusion is where you bring something together. Well, heat of fusion is sort of a misnomer in that way. This is just the energy needed per mole to liquefy a substance. So it is the amount of energy required to either get it to liquefy or come back into a solid state. In the same way, vaporization is the same thing. If you wanted to take steam and condense it down into a liquid, you would still use the heat of vaporization. Just it would be a different value. It'd be negative for exothermic process or positive for the endothermic process. So you can see in the picture here, if we wanted to go from a solid water to liquid water, we would use the heat of fusion, okay, and that would be endothermic. So you can see here that heat of fusion would be a positive number. It's positive because you have to heat something up, so you have to add energy, and also the heat of vaporization to go from liquid to gas. In the same way, that would be positive because you have to add energy to the substance to do that. On the other side of the fence, if you want to cool something down, if you want to take gas and go from a gas to a liquid, you're going to be using, again, the heat of vaporization, but it would be a negative number. You're going to take away heat. So it would be an exothermic process. Cooling it down is exothermic. Same thing, freezing it. You still use heat of fusion, same number, just be a different sign, be negative in that case. So heat of vaporization and heat of fusion are the things we're going to be using to calculate how much energy is required to break the intermolecular forces between the molecules to get them to the next phase. So from a solid to a liquid, we have to break that rigid structure, the IMFs that really hold them together. And then from liquid to gas, we have to completely break the IMFs that hold the molecules together. And then they basically are muted here, completely pointless. There's no IMF really at all keeping these gas molecules together. Here is another diagram that we use. This is called a phase change diagram as well. Sometimes people, I don't really like calling it phase change diagram because I just called that other one a phase change diagram, where we had all the liquid and gas. I'm going to call this a heating diagram, or heating chart. We're going to, whatever you want to call it, diagram, chart, doesn't really matter. This is basically a picture of what is happening to the temperature of our water in degrees Celsius as we add more heat. So you can see here that if we start at the water being a solid at negative 40 degrees Celsius, well, to get it to become a liquid, we're going to heat it up, right? So we're going to heat it up from negative 40 up to 0 degrees Celsius. Now, how would we calculate how much energy is required to do that? Well, you would use this, mc delta T. You would use mc delta T because the substance is not changing phase. Mc delta T assumes you're not having a phase change. So from negative 40 to 0 degrees Celsius, we're heating it up. The temperature is changing. And we're going to use mc delta T to calculate how much heat is necessary to do that. But as soon as we want to change from the solid to the liquid, we are not going to use mc delta T because when something is changing phases, it's not changing in temperature. That seems kind of weird and counterintuitive, but think about it this way. The molecules, if you think of it like a snapshot kind of thing here, it's showing right there, the molecules in the solid phase are rigidly lined up, but then at some point there's an amount of energy that is needed to break this up, to break all that rigid structure up. And so that is known as the heat of fusion, and there's no change in temperature there. The temperature is staying the same, 0 degrees Celsius. The only thing that we're changing is the arrangement of these water molecules. So when we are changing phase, there is no change in temperature. Again, that seems counterintuitive, but at the molecular level, there's no change in temperature. The gas molecules or the liquid molecules, the solid molecules are not changing in temperature. They're just getting additional energy necessary to break the IMFs, the intermolecular forces holding the molecules together. So we use heat of fusion here to calculate how much energy is needed to break the IMFs. And then as we go from a solid to a liquid, and we want to heat up the water to become a gas, to go steam, we again calculate the amount of energy necessary to go from 0 to 100 using mc delta T. Something I didn't just say, but the value of C here, the specific heat for water, is different depending on what phase it is. For liquid water, it's 4.18. For solid, for ice, it's I think around 2 joules per gram Celsius. And then as steam, I think it's like 2.06. I wrote it down somewhere, I just forget off the top of my head what it is. But same thing here, we're going to use mc delta T to calculate how much energy is needed to heat up the water as a liquid. And then as a gas, well, getting it from a liquid to a gas, we're going to use the heat of vaporization to calculate that. This is a big deal here. Notice the line here is much longer. Why would you think it's so much longer? Well, think about it this way. When you're a solid and when you're a liquid, the water molecules are all still pretty connected to each other. The liquid just kind of slides past each other, but the IMFs are still intact. You're still having that setup of the positive negatives. They just kind of move around a little more. But making something become a gas, you've got to completely destroy the IMFs. You've got to completely make those IMFs meaningless. There's no longer a significant connection or a significant attractive force holding the molecules together. So the amount of energy required to go from a liquid to a gas is a lot more. You can see here this is a much smaller amount of distance than this over here. It's almost double. And the heat of vaporization is much larger for water. I think it's 40 kilojoules or so per mole, while the heat of fusion is like 6 kilojoules per mole. So this is much, much bigger. And then lastly, if you want to heat up the steam even more, we would continue to calculate that using mc delta T. So one other thing to point out here that I wrote down, in these sections right here, the two phases exist simultaneously. So 0 degrees Celsius, liquid water, and solid ice exist at the same time. In the same way at 100 degrees Celsius, exactly 100 degrees Celsius, the liquid water and the steam exist at the exact same time. This isn't really like a critical point or a triple point or anything like that, but we're seeing the change due to the fact that we're seeing the change due to the fact that the IMFs are breaking. So we're adding additional energy, but the temperature of these molecules is not changing. They exist at the same time though. So let's go ahead and do a few examples of how we would calculate how much energy is involved in doing a phase change. So heat of fusion for water is 6.01 kilojoules per mole, and the heat of vaporization of water is 40.7 kilojoules per mole. Let's look at this question. For a 20-gram block of ice, how much energy is necessary to melt it? Now the equation that I would use to calculate this is right here. Q equals the heat of fusion times M. In this case, M is moles. Why is it moles? Because the heat of fusion is kilojoules per mole. So I have to make sure that my amount that's actually changing phase is in moles because the heat of fusion, that constant, is in kilojoules per mole. Let's go ahead and calculate that. So Q equals, the heat of fusion is a constant, 6.01 kilojoules per mole, times the number of moles, that's 20 grams of water. So I'll do that off to the side here. 20 grams of water. How many moles is that? Well, the molar mass of water is about 18.02. Calculator, where are you? There you are. So 20 divided by 18.02, and it's about 1.1, we'll do 1.11. So Q is equal to 6.01 times 1.11 moles. And that's really it. That's how you would calculate how much energy is necessary to create or to heat something up to get it to phase change. That's all. You really don't have to do anything more besides just that. It's a pretty simple calculation, just multiplying two numbers together. So 6.01 times 1.11, and we get 6.6711. Let's do 6.67. And that would be 6.67 kilojoules. Why is it just kilojoules? Kilojoules per mole, and then the moles cancel out. So I'm left with just kilojoules. That's the end. That's the end of that problem. Simple as that. Going to run through a few more. How much energy is required to vaporize 100 grams of water? Sure, that's all nice and... There we go. We're good. So in this one, we're taking liquid water and we're making it into steam. So how much energy is required to make the liquid water become steam? Well, same thing. Q equals, in this case, the heat of vaporization times M. Again, the number of moles of water in this case. So Q is going to be equal to, and then our heat of vaporization, what did we say it was? It was 40.07. So 40.07 kilojoules per mole times, and this is moles, so 100 grams of water, turn it into moles, 18.02. 100 divided by 18.02. 5.55. Hello, family. Oh, apple juice. Okay, so that's how I would calculate the heat of vaporization for this amount of water. 100 grams of water is 5.55 moles of water. So Q is equal to 40.7 times 5.55, and that's 225. Let's do 226. 226 kilojoules of energy. All right, this is the last problem I'm going to do. This is going to combine everything together. So we're going to actually think about, well, if I had a block of ice, how much energy would be required to get it from solid to a liquid, to heat it up to become steam, and then heat it up even more. So how much heat is required to get 250 grams of ice at negative 20 degrees Celsius to boil at 110 degrees Celsius? So ice at negative 20 up to 110 degrees Celsius. We're going to need to use these values right here. So we're going to need to use the heat of, or the specific heat of all phases of water. So the specific heat of water as a liquid, 4.18, as a gas, 2.03, and as a solid, 2.06. I've written those down for you. You should probably write those down somewhere, keep them handy when doing these problems. And I just wanted to make this quick kind of diagram of what we're doing here. So we are going to first calculate how much energy does it take to take 250 grams of ice as a solid and then heat it up to 0 degrees Celsius. After that, how much energy does it take to get 250 grams of ice to become a liquid? In this case right here, we're going to use MC delta T just to figure out how much energy is required to heat it up to 0. In this case, we're going to use heat of fusion to calculate how much energy is required to change the ice into a liquid. And then as a liquid, we're going to heat up that water from 0 to 100 degrees Celsius. We're going to use MC delta T to do that. And then to take that liquid at 100 degrees Celsius to steam at 100 degrees Celsius, we're going to use the heat of vaporization. And then we're going to continue to heat up that steam an additional 10 degrees and calculate the heat necessary to do that by using MC delta T. So kind of keep this in mind, MC delta T is used when there's no phase change, 0 phase changes. But when we do a phase change, we're going to have to use either heat of fusion or heat of vaporization, depending on what we're doing, of course. Let's go ahead and calculate this out. So for this one right here, Q is going to be equal to 250 grams of that ice times the specific heat of the ice, 2.06 times, and then we are going to get it up to from negative 20 to 0 degrees Celsius. So this is a change in temperature of 20 degrees Celsius. Next, we're going to actually heat it up some more, but at this point we're just breaking the IMFs, so we're going to use the heat of fusion to do that. And remember the heat of fusion, I wrote down 6.01. So heat of fusion is 6.01 kilojoules per mole. Okay. We have 250 grams of water, so I got to figure out how many moles that is. Okay, so 250 divided by 18.02, and that's 13.87. We'll just hold on to that 4 sig figs. 13.87. Now you might be asking, why didn't you change this to moles? Well, 2.06, that's joules per gram Celsius. Joules per gram Celsius. So I'm keeping the gram here because I want to make sure that all my units cancel out except for joules. And so, but over here, my heat of fusion is in kilojoules per mole. So I got to have the mass of the water in moles to do the calculation, right? So I get an energy unit at the end. You hopefully have figured out, but units are a super duper big deal thing in chemistry. You have to have it right or it doesn't work. One thing you're going to have right here is this is going to be in joules at the end of the day, and this calculation is going to be in kilojoules. So we're going to have to fix that later as well. So 6.01 times 13.87 moles of water. Next, I'm going to add in the MC delta T for the 250 grams of now liquid water going from 0 to 100 degrees Celsius. So 250 grams of liquid water going from 0 to 100. So it's liquid water, so its specific heat is 4.18. And then we're having a change in temperature of 100 degrees Celsius. And then we are going to vaporize that water. So we're going to break the IMFs completely. And so the heat of vaporization is 40.7 kilojoules per mole. And we're going to multiply that by how many moles of water there are, 13.87. We're not done yet. Adding in one more thing, that's heating up that steam from 100 degrees Celsius to 110 degrees Celsius. So still 250 grams of water. We're heating it up. We're going to use 2.03 as the specific heat because it's steam. And then it's going from 110 or 100 to 110, so it's a change in temperature of 10 degrees. Okay, so let's just write out all the numbers that we're going to get here. So Q is going to be equal to a lot of numbers. So the first number, 250 times 2.06 times 20. So our first number is 10,300. 10,300. Okay, and the next one is the heat of fusion value. So 6.01 times 13.87, 83.36. This is in kilojoules, this is in joules. I'm going to point out that right now. Next thing is heating up the liquid water, so 250 times 4.18 times 100. So 104,500. 104,500. This is joules. And then heat of vaporization. This is going to be a really big number. Heat of vaporization is going to always be a really big number because remember, you are completely destroying the IMFs between the water molecules. They are going to fly off from one another. There's a lot of energy that's required to do that. This is going to be 40.7 times 13.87. So that's 564.5 kilojoules. That's a large number. Last one, 250 times 2.03 times 10. 5075. Now that's in joules. I think I should have everything in kilojoules. So everything is going to be divided by 1,000 if it's a joule unit. So 10,300 joules, that would be 10.3 kilojoules. This many, 104,500 joules, that would be 104.5 kilojoules. There are 1,000 joules in a kilojoule. This is something we've talked about a bajillion times. Many of you have never learned this. Kilo means 1,000. So there are 1,000 joules to 1 kilojoule. Last one here, 5,075 joules, 5.075 kilojoules. There we go. So I'm going to add up these numbers. So my answer is only in kilojoules. And really, at the end of the day, people use kilojoules more. 10.3 plus 83.36 plus 104.5 plus 564.5 plus 5.075. Boom. There's our number. 767.7. So 767.7 kilojoules of energy. That is a lot of energy. I think it's like 8 sticks of TNT, something like that. That's a lot of energy to make ice become steam from negative 20 up to 110 degrees Celsius. So that's a big problem. Be ready for a problem like that in the future. Have an excellent day. I'll see you guys later. Bye.